Hi all, welcome back to Ashkemi. Since I was busy with my work, I was not able to give videos for some time. So today I've come up with the part 9 of the question paper discussion that we were so far discussing. For those who have not gone through the previous video, I created a playlist in the channel. So if you're interested, you can go through the playlist for previous videos. And without wasting much time, let's get started. The first question of this video is question number 32 of the question paper, which is about an analytical technique known as the AAS, which is known as the Atomic Absorption Spectroscopy. The question is about the material of cathode in hollow cathode lamp, whether it is tungsten, quartz, or element to be investigated, or all the above. So in order to answer this question, we need to have some idea regarding atomic absorption spectroscopy. So we'll have a short introduction on that. So in the slide, you can see a figure, which is the experimental setup for the same. And before moving on to the details of experimentation, we have to know for this atomic absorption spectroscopy is used. It is actually used for the determination of the concentration of an element in a solution or in a sample. So suppose you are having a sample which is having that sample is suspected to have some element. You can actually determine the concentration of the element, but you need to have an idea regarding what the element is, right? So therefore, if we talk about the principle of this type of spectroscopy, it is about you are having a sample and it is suspected that you are having aluminium in the sample. Then you can actually use this method to investigate how much of aluminium is present in the sample. That is concentration of aluminium present in the sample. And how can you determine that? And that is based on what is known as the absorption phenomena. That is, it is basically an absorption spectroscopy. So it is based on the absorption phenomena. That is, when you are passing some radiation, that can be a visible radiation or a UV radiation, whatever it is. So when you are passing a radiation through the metal that is present in the sample, it can absorb this radiation. That is, normally when the element is in the ground state, it can absorb the energy from the radiation to get excited to the excited state. So some amount of radiation is being absorbed. So if you are determining, or if you are finding out how much of radiation is absorbed, then that absorption will be definitely proportional to the concentration of the element in the sample. Okay, so this is the principle of atomic absorption spectroscopy. So the most important thing is that here you need the material in the atomic state. That is, if you are provided with a particle. So if a particle is your sample, initially you have to break that particle into molecules, and again you have to convert it into atoms. Atoms in the gaseous state. Then only you can analyze it using atomic absorption spectroscopy. So this is the principle in a nutshell of atomic absorption spectroscopy. Now coming to the different parts of atomic spectroscopy, atomic spectrometer, atomic absorption spectrometer, you can see that the first part is a hollow cathode lamp, and our question is mainly based on this part, hollow cathode lamp. So this is the source of light that we use. Okay, this is the light source that we use in this type of spectroscopy. So hollow cathode lamp, it is actually a combination of a cathode and an anode. Okay, and the cathode and the anode, they are enclosed inside a cylindrical glass tube. You can see that this is a kind of cylindrical glass tube. So it is actually having a cathode as well as an anode. Now, what material is used to make this cathode and anode? Anode is usually element tungsten. Okay, but the cathode is made up of the element to be detected. So this is the light source. Hollow cathode lamp is the light source of atomic absorption spectroscopy. It will be having a cathode as well as an anode, which is enclosed inside a cylindrical glass tube. Anode will be usually tungsten, and that is same for all experiment. But the cathode will be different for different experiments. Suppose you want to analyze aluminium, you have to take that element as the cathode. And that is actually what is asked in the question. That is, the material of cathode in hollow cathode lamp is constructed in, the answer is option C, which is the element to be investigated. So this is all about the question, but we'll have a further discussion on the other parts of the spectrometer as well, because that may be asked in some other exams. Then it will be more useful if you have an idea regarding that too. So we'll have a discussion on that. When you look at the other part, next part, it is actually a combination of a nebulizer and as well as a atomizer. So first we'll see what is a nebulizer. Nebulizer is a part of this AAS where the sample solution, you'll be having a sample solution, that is a liquid solution. So in this you'll be having the sample too. And that sample or the element that is to be determined, that sample is actually converted into an aerosol. Okay, that is converted into aerosol, so that you can spray that aerosol into the flame. And that aerosol is actually the conversion of the sample solution into aerosol is actually done by nebulizer. And after that, nebulizer will mix the aerosol of the sample with the oxidizer and the fuel, and it will be sent into the flame. So nebulizer, it actually mixes, it converts the sample into an aerosol, and it mixes the aerosol with an oxidant as well as the fuel that is for heating, and it is then sent into the atomizer. You can actually see the inlet for the fuel gas and oxidizing gas, and both these are mixed with the aerosol and it is sent into the flame. So this place where you have the flame, that is actually known as the atomizer. Okay. So this part of the instrument that consists of a component which is known as the atomizer. And the function of atomizer is actually to convert the sample, the element present in the sample, into atom. Okay, so we need the sample in the form of atom, and this is actually done by the atomizer. So initially I've already mentioned that when you are having a particle that is converted into molecule, and the molecule is further broken down into atom, and that is converted into the atom in the gaseous form. So when you are when you are making this aerosol and mixing it with oxidant and fuel and send it to the flame, it actually produces the atom in the gaseous form. And that is the important, these are some of the important components of AAS. Now you can actually see a monochromator. Monochromator is something which helps in the selection of a radiation of a particular wavelength. That is, if you are having a radiation with a range of wavelength, you can actually select the radiation of a particular wavelength, say lambda, so which is characteristic of the element that is to be detected, and that particular selection is actually done by the monochromator. So only the radiation of that particular lambda will be interacting with the atoms of the element that is to be detected. Then you can actually find out an absorption. So see an absorption which is a function of concentration. That is, that absorption will be proportional to the concentration of the element in the sample, and then that is sent to a detector, and finally you will be getting the result or the output in the form of a graph, and that graph is actually a plot of absorption versus concentration. Okay, so this is the graph that you can actually if this is the shape of the graph. I'm not aware about the shape of the graph. but this is what you plot, that is absorbance and concentration. So this is the graph that you get. But there is something which is known as the calibration of the instrument, so we'll have a discussion on that too. So I think you're now familiar with the various parts of this atomic absorption spectrometer and the function. So I have said about something known as the calibration curve. So we'll see what is a calibration curve. Okay, so before we start with an atomic absorption spectroscopic study of a particular sample, initially we have to construct a calibration curve. For example, if you consider you want to analyze a sample of lead. So you want to know how much of lead is present in that sample. So for that, initially you have to construct a calibration curve with a concentration, absorbance versus concentration for known concentration of lead. That is, you have to consider different known concentrations of lead. That is, for example, if 10 micromolar, 20, 30, 40 micromolar of lead solution is analyzed and its concentration is determined. So you'll be getting a calibration curve. Okay, so you'll be getting a graph like this for non-concentration of lead, and this is known as the calibration. Now you'll be analyzing the unknown sample, that is sample which is having unknown concentration of lead, and finally you'll be getting the result as a absorption, that is the lead present in the sample will be absorbing the radiation, so you'll be getting an absorption. Now you can actually find out that absorption from this graph. So this is 1, 2, 3. So if it is having an absorption of 1, you can actually extend this absorption of 1 to the concentration, and you can see that it comes in between 10 to 20 millimolar. Okay, so if the graph is having all the calibrations, you can exactly find out the concentration. Maybe it will be a 12 micromolar or 12 millimolar, then that will be the concentration of the lead in the sample. So this is how you make use of a calibration curve to determine the concentration of the element in the sample. So this is the importance of AAS. You always need a calibration curve that need to be constructed before analyzing a sample. Now coming to the applications of AAS. The importance of AAS is that you can actually analyze even trace amount of element in a sample. So that is the main importance of AAS, and the element that are mostly determined using AAS are lead, mercury, calcium, magnesium, etc. And moreover, the areas of applications are in environmental studies, especially in drinking water, analysis of drinking water, soil, etc. Then in food industry, in pharmaceutical chemistry. That is, in pharmaceutical chemistry, you can find out the concentration of element in some drugs and all, and in foodstuff, and in environmental studies, etc. So these are some of the important applications and importance of. So I hope this portion is clear to you. So these are some of the important points regarding AAS that is usually asked in exams. So if you have got any doubt, you can just comment in the comment section. I'll be answering according to my convenience. Okay, so let's move on to the next question. Next question is a pretty simple question about cell constant. Cell constant is actually a ratio of length by area. So option B is the right answer. And if you are asked to determine cell constant, you can actually make use of a method which is shown here. That is, cell constant can be determined as a ratio of conductivity and conductance. That is, if it is more convenient to obtain the value of cell constant by measuring the conductance of standard solution whose conductivity is known, then that can be applied as a method to determine cell constant. And cell constant is usually represented by a symbol known as G star, and the unit of cell constant is centimeter inverse. That is, unit of length is centimeter, area is centimeter square. So when you cancel out centimeter from the numerator and denominator, you will be left with centimeter in the denominator. So that is how you are getting centimeter inverse as the unit of cell constant. So this is a pretty simple question, and we make use of standard solution KCl for determining the cell constant. Okay, so let's move on to the next one. So the last question of this video is from organometallic chemistry, mainly about the olefinic hydrogenation using Wilkinson catalyst, and you are asked to find out the initial step of this mechanism. So for that, we need to have an idea regarding the mechanism of the reaction, which is given by this Tolman catalytic loop. So these kinds of loops are known as Tolman catalytic loop, which is somewhat cyclic in nature. That is, you'll start from one end and finally at the end of the reaction, the product gets eliminated and you'll regenerate the catalyst again. So when you consider the olefinic hydrogenation reaction, you can just represent this reaction like this. That is, you will be having an olefin to this hydrogen molecule is added so that it reduces to a alkane. That is, it will be converted into a saturated compound. Now when you consider the different steps involved in the reaction, the reduction actually takes place on the surface of the catalyst. So this is Wilkinson catalyst, which is a square planar complex of rhodium with a 3 triphenyl phosphine ligand, which is represented as P in this figure, and one of the ligand is a chloride ligand. So when the reaction initiates, so you need some place to add the substrate. That is, substrate is actually the olefin, and hydrogen is actually the one which will reduce this olefin. So for that, you have to create a vacant coordination site, which is formed by the dissociation of one of the triphenyl phosphine groups. So here you can see that a vacant coordination site is being created. And now in the second step, hydrogen molecule is added, and that step is known as the oxidative addition. So this comes out to be the second step of olefin hydrogenation using Wilkinson catalyst, and hydrogen is added, and after that the olefin is added, and that will be occupying the vacant coordination site. Okay, now once the hydrogen as well as the olefin is added, then 1,2 insertion, that is addition of hydrogen to this olefin, that is, then only it can get converted into alkane. So that happens, and that is known as the 1,2 insertion. After the 1,2 insertion, when the alkane is ready, it is eliminated from the catalyst, and that step is known as the reductive elimination, and this will again recreate the vacant coordination site. Now that can accept the one of the triphenyl phosphine group to regenerate the catalyst. Again, by the dissociation of triphenyl phosphine, the reaction continues. So this is a cyclic reaction. So the important steps involved are phosphine dissociation, oxidative addition of hydrogen, olefin addition, 1,2 insertion, and reductive elimination of the product. So in the from the mechanism, it is quite clear that the phosphine dissociation from the Wilkinson catalyst, the initial reaction, that is, the reaction initiate with the dissociation of phosphine ligand from Wilkinson catalyst. So this is all about this question. So I'm sorry that this is the last question. The previous one is not the last one. So question number 35 is the last question for this video, which is about some spectroscopic techniques. That is free radical, the spectroscopic technique that can be used for analyzing or detecting free radical. You are asked to find out which one of them is actually used for that. Option A is mass spectra, B is CID-NP, C is UV spectra, and D is Mossberg spectroscopy. So when you consider the free radical, you may be confused with the option 1, because mass spectra, in mass spectra you can actually see free radical, right? But the point is that in mass spectra you need the radical cation. That is very important. They are not actually simple free radical, but they are radical cation. So therefore you can rule out the possibility for mass spectra. In mass spectra, radical cation is required. So this will not be the option. Now coming to UV spectra, you know that is mainly used to find out the type of chromophore that is present in a compound, like whether it is a double bond, a triple bond, or triple bond, or whether it is a carbonyl group, etc. You can get an idea about these chromophores in UV spectra, but they are neutral compound and not radical, so you can rule out the possibility for UV spectra as well. Now coming to Mossbauer spectroscopy. Mossbauer spectroscopy is actually used for the analysis of especially elements like iron. That is, in mineralogy, it finds application in determining the valency of metal, that is especially iron. So in this, the main principle is that you will be analyzing the solid sample with the help of gamma radiation. So you will be passing gamma radiation through the sample, and then the amount of radiation transmitted radiation is then analyzed. So here, since it is mainly involved in determining the valency of the metal, it mostly involves the cation, we can say Fe3 plus or Fe2 plus, etc. So this, you can also rule out the possibility for Mossbauer spectra. Now coming to option B, which is somewhat a rare type of phenomena. What is so you need to understand what is CIDNP. It is usually pronounced as kidney. Kidney is actually a nuclear, it is a type of NMR technique, that is nuclear magnetic resonance technique, that is used to study chemical reactions involving radicals. I'm not going into the details of that. So we'll just have the expansion for CIDNP, which is chemically induced dynamic nuclear polarization. So this is the expansion for CIDNP. Okay. And this is a basically it is an NMR technique for studying the chemical reactions involving radicals. So most probably this is the right answer, option B. So that's all for this question. So that's all for this video, and I hope you'll find it useful for the coming exams. And if you like this video, please do subscribe and share. And I'll be coming soon with the next part of this video. And I wish every one of you a happy Vishu and an Easter. And stay tuned for the next video. Thank you.